All right, so these are a set of four um, rotational problems I think are fairly reasonable. They're going to go over some different concepts, and they're ones where I'm hoping will be either proportional enough or not using math that's so ridiculous where we would think that they would not show up on this year's AP exam. So sorry about the quality of this, but in order to upload it, I've got to have kind of a crappy quality video. Um, so round objects, and this should say 3. Hoop, cylinder, um, and sphere, and that's a solid sphere, I guess we could say, are rolling down a hill of height h and angle theta. Determine the linear speeds at the bottom of the hill if there's minimal friction, but enough friction to cause them to roll and not to slide. So if there was 0 friction, these would all slide down. There'd be no rolling component, and they would end up getting to the bottom all at the same point in time. All right, so there's also a particle of mass m, and it's going to slide down with negligible friction. So I'm going to do the particle first because that's the easiest. This is an energy problem, so think energy. So initially, at least, what we've got, and I'm going to move this a little bit. Sorry, trying to get my setup okay. Okay. For the particle, I'm going to think about the energy at the top is going to be equal to the energy at the bottom. E initial is equal to E final. Well, what do we have at the top? At the top, we've got gravitational potential energy. And it's hard to see that's an H, so we're going to say U grav at the top. Kinetic energy we're going to have at the bottom. There's other ways you could say that, like you could say U initial plus K initial equals U final plus K final, things like that. I'm simplifying this down. So I'm going to say here our particle was of mass m, g, the height was h. Hey, that looks like the general formula actually. This 1/2 m maybe would be a VF, V final squared. I'm just going to use that. All right, so if you notice that for this particular equation and a lot of energy equations, the mass cancels out, so that's not that important. So I'm going to get 2gh equals v squared. So v radical 2gh. I'm going to probably reword this saying, please answer in terms of m, g, h, v fundamental constants or something like that. So, okay. So now I'm going to look at the hoop. The hoop, the cylinder, and the sphere are all going to be similar how we're going to think about it. So here I'm going to think energy again. E initial equals E final. And here I'm going to still have U grav, but at the bottom part of the hill, these things are going to be rolling in addition to moving linearly. So they're going to have KE plus KE rotational. So I'm going to think about this as M, that should have been a capital M, GH is equal to 1/2 mv squared plus 1/2 I, rotational inertia, omega squared. Now, that's a lot of different terms. So, and again, I probably want to revise this before I get it out to you. It'll be this, it'll be linear speed, I think. So something like that. So now I'm going to want to think about what this is. For a hoop, or anything where the mass is all on the outside, it's going to be mr squared. Okay. And we can also relate the idea, and this is pretty important and something I would have written down somewhere where it's easy for you to convert back and forth between linear and angular terms. So velocity is equal to omega, or angular velocity, times the radius. You can also think of the radius as equal to linear velocity, pardon me, angular velocity is equal to linear velocity divided by the radius. I would write the same things down with acceleration and angular acceleration, and displacement and angular displacement. I'd have all those, basically 6 little mini formulas written down to help you if you need them. Don't know if you will, but couldn't hurt. So thinking about that then, I'm going to use this and this to plug in here now. So I'm going to do this again. I'm going to say mgh equals 1/2 mv squared plus 1/2. So this is going to be mr squared. So that's the moment of inertia there. Omega squared is going to be v squared over r squared, because it's capital R in this case. So now I get to do some nice things. I get to cancel some stuff out, and hopefully you know how much that pleases me. So I've got an r squared in the bottom here. I've got an r squared in the numerator over here. So now I'm going to rewrite this, and I'm going to say mgh equals 1/2 mv squared plus 1/2 mv squared. mgh equals mv squared. And again, I can cancel some things out. The mass does not matter here. So I get that my velocity here for the hoop is equal to that. I can do the same things again for the cylinder and the sphere, except they're going to have different moments of inertia. So I wish I had different colors than these, but this is what I've got right now. So I'm going to put these over here, and I'm going to say I cylinder is equal to 1/2 or 0.5 mr squared. I sphere for a solid sphere, 2/5, or I'll do that. And all I've got to do is substitute those in for this. So that's kind of what I'm going to do down here. So for a cylinder, I'm going to start at this middle spot right here. mgh equals 1/2 mv squared plus 1/2 mr squared v squared over r squared. I don't know why I did the fraction that way. And once again, we're going to be able to find out that this cancels out. And lo and behold, what I'm going to get now is mgh equals 1/2 mv squared plus 1/2 times 1/2. So that's 3/4 mv squared. Cancel, cancel. So we're going to find 4/3 gh square root of that is going to be equal to v. What about a solid sphere? I'm going to move on up. Hopefully this can be seen in here. mgh equals 1/2 mv squared. Taking a look at the formula I had earlier for the cylinder. Plus 1/2 2/5 mr squared v squared over r squared. And what I end up getting here is mgh and 1/2 squared plus, okay, this is a little bit more annoying math-wise, 1/2 times 2/5, 2/10, or 1/5, I guess. So that's 0.5, that's 0.2. And masses cancel out. It's a little bit annoying here with this, but, oh shoot. I could have left this in fractions, I think might have been a little bit better, but we'll worry about that, just from a comparison standpoint. I'm going to give you the math. It's 1.42. I said I wish I would have done that a little bit differently. All right, so something like that. This would be 1.33. And that's radical 2. So what the heck does that mean? Well, it agrees with what we would think, which is that the particle will get down there first. How do we know? It has the highest final speed. So radical 2 GH. Here, this has the next highest speed, radical 1.4 GH. Here, this has the next highest speed, radical 4/3 or 1.33 GH. And the hoop has the slowest speed, just radical GH. So that agrees with the idea that this has the greatest moment of inertia, middle, least moment of inertia. And the particle, which doesn't have any rotational energy at all at the bottom, gets down there the fastest. Okay. So that's the first one, and I will upload a PDF of that as well. This is from 2004, APC Exam Mechanics 3. I'm doing only parts A and B of that to get to the idea of parallel axis theorem. So that idea, I always forget whether theorem is spelled with an EM or an OM, so you can make fun of me with that, which is fine. But basically what we end up doing is anytime you have something rotating where its axis of rotation is not at the center of mass, we're going to have extra inertia. In other words, it's going to be tougher to change its rate of rotation. So a uniform mass rod of mass m, length L, is attached to a pivot of negligible friction, as shown above. The pivot is located distance L/3 from the left end. Express all answers in terms of given quantities and fundamental constants, blah, 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 blah. Calculate the rotational inertia of the rod about the pivot point. So first of all, if this is a uniform rod, which is what it says here, then what I've got to think about is that center of mass is going to be in the center. That's its center of mass. So it's rotating at a certain distance of its center of mass. Well, if this is 1/3 of the way, and that's half the way, this distance here would be L/6, or 1/6 the length of that rod. So in general, if I want to find out the moment of inertia, I total equals the moment of inertia about the center of mass, which I'm going to say is Cm, and then I'm going to add what I call extra, which is due to the parallel axis theorem. Okay, so the parallel axis theorem basically says however far you are, you always treat that as a point source, because we've already taken the shape of whatever this is, be it a hoop, a solid rod rotating about the center, or cylinder or something like that. We take this into account here, where we find its moment of inertia about its center of mass. Okay, so this is going to be I extra simply md squared. Now, a lot of times this is written as an r, but I'm going to say it's a d only because that's the distance from the center of mass to this other location. So I want to avoid a lot of different r's or uses of the same variable. Okay. Now eventually we're going to put these variables in terms of L and M and stuff like that. So right now then, I'm going to say this. For a rod rotated about its center, it's 1/12 ml squared. Now, you might not know that off the top of your head, and many times what the AP will do is they'll give you some things like that. Notice they didn't give you that here. So this year, I would have that table written down or have your book open to where you have all those different shapes. At one point, the AP actually did ask you it basically told you that the moment of inertia of a solid rod rotated about its center was 1/12 ml squared, and to use the parallel axis theorem to derive the moment of inertia about the left end here. And it was awesome. It came out to be exactly the same as what the given was, which was 1/3 ml squared. At any rate, in this case, 1/12 ml squared, and that's if rotated about the center. Okay, so I'm going to say this 1/12 ml squared. Now this extra is going to be md squared, but what's that distance? Well, it's L over 6. So I'm going to say m L over 6 squared. So now let's go back and do that math. 1/12 ml squared plus 6 squared is 36, so that's going to be 1/36 ml squared. Hey, those have common denominators, so this would be 3/36, 1/36. That's 4/36. So it's going to be 1/9 ml squared. Okay. So that's an example of the parallel axis theorem. I added this other, or left this other part in. So it says assume that the rod is released from rest, position up here. So that's where it's pivoting about. And calculate the linear speed, of the bottom end of the rod. So that would be this, when the rod passes through the vertical. So essentially what we've got is we've got this thing coming down here, but it's going to rotate about this. Now this is what's kind of interesting. This distance here is going to be 2/3 L. Okay, but if we think about this as an energy problem, the rotational kinetic energy that this thing is going to get is going to be due to this center of mass falling, and that's only going to fall 1/6 L. So it's a little more complicated than it seems initially. So I'm going to write that down. I'm going to think of that as an energy problem. So again, I'm going to say E initial is equal to E final. What do I have here? I have gravitational potential energy. Down here, I've got rotational kinetic energy. Okay. Well, what is KE root? 1/2 I omega squared, right? Now the thing that's interesting here is it's asking about the linear speed of this. Once again, we've seen before, we can do that, or now we got to be a little careful about this. And this is what I was mentioning up here. This distance, this radius, is the radius from the axis of rotation. Well, that axis of rotation is this distance, 2/3 L, from the end of the rod. So that's going to be a little bit sneaky. So I'm going to worry about that at the end. I'm not thinking about that right now. So here I'm going to have the general formula for this is mg delta h 1/2 I omega squared. Okay, so what's my delta h? Well, the delta h is going to be this L over 6, which is the change in height of the center of mass. So it was mg L over 6, 1/2. We already figured this out, is 1/9 ml squared. And then what we're going to say is omega squared, and that's really going to be V over R. And I'm leaving this as R squared. I'm not fixing it yet, because I want to see what things I can cancel out first. So I can get rid of an M on each side at this point. So I'm going to have GL over 6, 1/2 times 1/9 is 1/18. L squared V squared over, now this is where I'm going to have to add this in. This is going to be 2/3 L, and that's going to be squared. Oh, that's a bit annoying. Right? Well, one thing I can do here is this is in the numerator, that's in the denominator. So get rid of that. L squared is gone. This is in the denominator, but this is in the denominator of a denominator, which is like the numerator. And remember, these numbers are squared. So let me go through again and see what I've got. GL over 6 equals 1/18. Okay. 3 squared is going to be 9, and that's going to be in the numerator. I'll put that in parentheses. 9 V squared. 2 squared is going to be in the denominator. So that's 4. I think I'm doing this right. So there's a lot of numbers here I can reduce. So this is kind of annoying. I don't think they'll ask you to do this much numerically in this year's AP exam. So 9 over 18 is 1/2. 1/2 times 1/4 is 1/8. So I get GL over 6 is equal to 1/8 V squared. Well, we can reduce those by a factor of 2, right? So GL over 3 is 1/4 V squared. So now I'm going to try to, sorry about that. So now I'm going to try to multiply through. So this would be 4/3 GL is equal to V squared. So I'm going to say radical 4/3 GL is equal to V. Then maybe they want you to simplify that as 2 times GL over 3 is equal to V. I don't think at that point it would matter. And again, I don't think here that's that big of a deal. So I was really looking at the first part of this problem most likely, because I did want to do an example of the parallel axis theorem, but this bottom part, kind of interesting also, and again, I'll get the PDF to you. Okay. This one right here is a modified from problem 70, chapter 12 of your textbook. Oops, sorry about that. Again, I gotta think about this. Ugh. Okay, so I'm going to show you a sneaky way to do it and a little bit more appropriate way of doing this as well. And the sneaky way, it might be okay this year, as long as you can write down things. So you've got a surface of negligible friction here. You've got a mass of 2m up here, a mass of m down here, pulley, which we're going to assume is a solid cylinder of mass m as well. And so if this pulley had no mass, this is a super easy problem. Acceleration is going to be net force over total mass, so it would be mg over 3m, right? So it would basically be g over 3. But it's not that simple when we have something like this. So you want to think about the systems that you've got that are involved here and recognize that you're going to have acceleration constraints. So in other words, the acceleration of the pulley here, or pardon me, the rope here would be equal to the acceleration there, even though the tension in these may not necessarily be the same. In this particular case, when you've got a mass in this particular system. So I'm going to think about this system here, and I'm going to say a couple things. I'm actually going to do this in my simple way first, then I'm going to pause and I'm going to combine the two videos together. So we'll hold off on this in just a minute because this video is getting close to 30 minutes. I want to upload one while I make the next one. Okay, so over here, we know that A is equal to net force over m total normally. But in fact, what we would want to think of here is not m total, not 2m plus m, but equivalent mass. If this is a solid cylinder and you recognize that the moment of inertia is 0.5 mr squared, if that rope is pulling on the outside of radius of it, then this only acts as if it has half a kilogram of mass. So I would say A equals F net over M equivalent. And we'll do that. So in this case, this is going to be mg over 2m plus this m plus this is equivalent to half a kilogram, 0.5 m. Okay. So when I do that, I get A is equal to mg over 123.5 m. The m's cancel out, so it's going to be A is equal to g over 3.5. And you can do that in meters per second squared if you needed to. Okay, so like I said, I'm going to stop that before the 30-minute mark because that seems to be the limit of what I can upload in a reasonable time. And I'll combine those two